Okay, so let us discuss about today's concept, which we would be learning about polygons. Polygons. Okay, so basically polygons are my figures which follows having straight line segments and having straight line segments closed. They must be closed, and they must not and the segments must not intersect. So these are my three conditions for a mathematical figure of any sides to call it to be a polygon. Let us quickly see which of the curves are polygons and which are them not. So let me draw few of some figures here. Let me just quickly draw, then it will be illustrating to you more accurately. Let me draw three sets of figures which are polygon and three sets of figures which are not. Since I am being drawing it roughly, so you may just remove the exception if the sides are not being very clear to you. So let me call these curves that are polynomial, not polynomial, polygon, sorry. Okay, and there are few sets of, not few, major sets of my figures in my mathematical dimension to whom I may not call polygons. Figures like and the last one. So these are few of my figures which I have drawn for letting you illustrate which of the curves I can say that are polygon and which are not. So see, these three polygons which I have categorized under the category of a valid polygon obeys the three laws I have just stated. Seems clear? So see, let's discuss about curve 1. I have four edges, four straight line segments. If it doesn't seem straight, then it's my fault. It's basically rough sketch, so you may just neglect that small issue. Seems clear? Yeah, since I'm been drawing a broad scale, that's why. So while you will be drawing in your tests or exams, you would be having a perfect straight segment. So I'm occupying the usage of four straight line segments, and the figure is closed, and any of the edges are not intersecting. So this curve would be my closed polygon. This curve too, I have utilizing four sides having closed in their edges and they are not intersecting. Further, this polygon I can easily state that it is also closed, as well as it is the edges of which are not intersecting. So I am been calling all these my polygons to be what? A valid polygon. While see, here comes the scenario where you are having an exceptions of cutting two edges. So any point where the intersection of edges happens, one may not be considering it to be a valid polygon. Seems clear? So it is not a polygon. And here also you may see the edges are also cutting, edging are also intersecting, as well as the figure is not closed. So thereby we would be not considering it is a polygon. Can you just guess why this shape or a curve is treated as not polygon? Can you just guess? Yeah, please go ahead. Since the image is not closed, since this image is not a closed one, what if I would have an image like this? Would it still be a not polygon, or it can be a polygon? If I just attached one end with this end with a straight line, remember I have connected with the straight line, then would I be calling it a polygon or not? Yeah, since now it is being closed, as well as all edges are not intersecting and all edges are straight, so I would be calling this figure to be a polygon. Okay. But for the time being it is not, so I am removing those two connecting edges. So don't mind. Okay, so let us now continue our discussion about classification of polygons. Okay, so I have basically two types of polygons. What are they? One is my convex polygon, another being my concave polygon. Okay, and see, polygon can be of, starting with the three sides. I can have a polygon be drawn like with using three sides. I cannot have a polygon with two sides or less than that, since I cannot draw a closed figure using my two lines anyhow. So I would require at least three sides for calling it to be a polygon, as well as I can utilize the usage of four sides. Okay, and though I can also utilize five sides for being a closed polygon, as well as I can also utilize my six sides for calling it to be a six-sided polygon. Seems clear? And further up till you may extend up to infinity. Yeah, you may extend up to infinity. Can you imagine? Yeah, you may just draw. Can you just draw an 9-sided and 11-sided polygon? Can you just draw it in a copy and just cross verify have you been able to draw or not? Can you just please check? Yeah, go ahead. Okay, so I think you are done with, and you are truly been able to draw on it. I think so. I hope so. So let us now continue our scope of discussion using for our convex as well as concave polygon. So see, convex polygon and concave polygon. See, let me illustrate through a concave one. It is a special one. Let us know about concave first. After that, we would be turning towards convex. So see, if I would have a polynomial, let me draw a special polygon, something like this. Can you just guess how many sides this polygon have? Can you just guess? Can you just see? Yeah, it is 1, 2, 3, 4 and 5. Okay, so it is a 5-sided polygon. Okay, let us now see. We would be also naming these 3-sided, 4-sided as well as 5-sided up to 10-sided polygons. They are having their special names, like 3-sided have a triangle, 4-sided is being known to its quadrilateral, 5-sided being a pentagon, and further which we would be learning about in a while. So let us now discuss about the concave scenario. So here, how do I determine concave? If in my polygon, if I connect any of the edges and draw a imaginary line segment, and if that line segment, it is known as the line segment test. Okay, line segment test. Basically, in my line segment test, what I would be observing, if the imaginary line which I've been drawing lies outside of my polygon, outside of my polygon, see, the word is very important, outside of the polygon, then my polygon would be named as concave. Seems clear? Concave polygon. Let me illustrate you using various examples. Shall we move ahead? See, if I just draw this line segment, see, interior of my polygon includes the region of this, only this. I would be calling my interior of my polygon if any of the point or a line segment lies in my pink shaded region. Except this, I won't be calling it interior of my polygon. So here the green line, which is my imaginary line, I have just connected two of my edges, and if the imaginary lines lie outside of my polygon, then I would be naming it as concave. So the given figure is a concave 5-sided polygon. Okay, concave 5-sided polygon. Let us know few of the concave ones. See, let me draw. I also have a polygon like this. Let me draw side more clearly. Clear? Again here, if I just join these two, would I get a line which would be lying outside of my polygon? Can you just guess? Can you just guess? If I join these 2 points, I would be having a polygon lying outside. Sorry, I would be having a line segment which is lying outside the polynomial. Is it that the case? Yes, it is that the case. So if I just join it, my polygon, my line segment will be coming outside the polygon. See, if I take these 2 line segments, then my line segment would be inside, but I have to consider for all my cases. If at any of the case my line segment is going outwards, then I won't be calling it as what? Concave. So, and if now let me just illustrate about the convex polygon. Convex is my one where the line segment test fails. Okay, it is very clear. Now let me draw an image. Let me draw a polygon. Let me be like this. This is a 4-sided polygon. Okay, 4-sided quadrilateral, which we are naming it as quadrilateral. So here, if I just connect any of the 2 vertices, be it like this and this, if I just connect, let me connect these 2 vertices. If I connect these 2 vertices, my imaginary line is lying inside of my polygon, so I won't be considering it for calling it to be concave. And let me check with another sets of vertices to call, like let me consider, wait, let me just remove the vertices. Okay, so I haven't failed till now. Let me using this and this. Again, if I join these 2 edges, again I am getting a line segment which is lying inside my region. So again my line segment test is failing here in this case. Let me test for another 2 vertices. It might get failed using another sets of vertices, since we are not done with. Let us suppose I have opted for this and this. I have also opted for this and this. So now let us just consider adjacent ones. Let me just consider adjacent ones like this and this. Okay, and if this and this I join, it is the same side only. It would be lying over the same side only of the polygon. It won't be lying outside of my polygon. It would lie on the boundary of my polygon. Seems clear? Yeah, it won't be lying outside as well as inside. It would be lying outside as well. So we won't be considering it to fail my line test. So if you opt for any of the two vertices, and join here, you will get again a straight line which is on my boundary of my side edge of a polygon. So here my line segment test fails. Which was stating if an imaginary line lies outside of my polygon for any of the two given vertices, I can say that the polygon is my concave. So, but here they are not any of the two vertices which would yield an imaginary line which would be lying outside of my this pink shaded region. Seems clear? Clear till now? If you have any issues, you may just pinpoint at any of the time. Until now, it's clear. Shall we move ahead? Yeah. Okay. So this is my basic convex and concave. So let us now move our discussion to let me quickly let you what is regular polygon and what are not. See, I can say a polygon to be regular, likewise if I need to draw a polygon like a triangle, since my triangle all sides are equal. No, it may not be. If my triangles all sides, since it is an equilateral triangle, if I have all sides equal and all sides equal, see, for considering a polygon to be regular, I would be considering all sides and all angles to be equal. Seems clear? Yeah. So if I have a triangle A, B, C, if and only if my angle A is equal to angle B is equal to angle C, okay, and my edge AB, which is my this edge, if this edge AB is equal to with BC, and which in turn equal to CA, then only I can say this three-sided polygon to be a regular. Seems clear? Yeah. So let us go ahead and using towards our next property of polygons, which is my sum of the measures of external angles of polygons. See, I won't dictate the a concept like a dictator. I would be rather happier to let you know using a simple illustration. Okay, so I have a triangle. Let me draw polygon. Wait. Not mine. So the property name is name of my property is what? Sum of exterior angles. So let us now see if I have a polygon A and here being a polygon B and it is C. So what would I do? let me mark A here. What if I just extend my polygon. See, I had AB length, I had AB line segment here, okay, which is this line segment is my AB, this line segment is my AB. So let me just extend my line segment like this only, extend up to here, and let me mark an angle. I am assuming the angle to be what? 125 degrees. Seems clear? Similarly, as I extended my AB, let me extend BC line segment. Okay, let me also extend my BC, which would be like this. Again, don't mind if the line segment, yeah. So I have my angle X here, X degrees. Okay, and it was what? It was my B. It was my C. Similarly, let me extend CA. I would be having like this. And that angle is also my 125 degrees. Okay, so these are my external angles. I would be calling these angles, if I just extend my each of the line segments, which would be forming a closed polygon, I would just be getting by all the external angles. So I can say that this angle, which I would be shading, let me shade it with another color. So this angle, as well as this angle and this angle, all these three angles, all this signify external angles of my polygon. Seems clear? Clear till now? What are external angles? Yeah, so my property states that this is my property, that sum of all the external angles, all my external angles of a closed sided polygon would be what? Would always be 360 degrees. Okay, yeah, so let me illustrate. So could you just find about, wait, so could you just find about the value of X here, which is illustrated in the question using the same property? Can you just pause and find? Yeah, I would be solving here for you. You may just cross check whether you are getting the same value for X or not. You may go ahead. Yeah, so let me just solve for X. See, I have external angle C. Okay, this external angles I will be considering external, not the internal ones. External A plus my external B plus my external C would sum up to what? 360 degree. That's what my property says. So external of A angle is given to be 125, as well as my B is also 125. C I am taking to be X, and here 360. 125 would give me 250 degrees plus X equal to 360 degrees. So if I just subtract 250 from my both of the sides, LHS and RHS, I would be having equation like this. further which I simplify, I would get x degrees, how much? 110 degrees. So I would be having a measure of 110 degrees at an exterior of my C. Okay, so this is how we would find our external angles. So do you need the proof of it? Do you need the proof of it? How we always consider our sum of our external angles to be 360. We would discuss it somewhere later. Till now, let's keep our scope of discussion up to about the application of the statement, rather going in that proof. Okay, we would be discussing somewhere later. Okay, so let us now just take up a question. It is given that I have a regular hexagon. A regular hexagon is a simple closed regular six-sided polygon. So let me draw a six-sided polygon, which would be like this. Seems clear? I have regular, so it means, let me mark first labeling A, B, C, D, E and F. That I have all the edges to be of equal length, and if so, I also have all my angles to be of equal measure. All the angles of my equal measure. Okay, though it may not seem to be in equal measure, but for now consider to be all of them being equal. So it is my regular six-sided polygon. So I have to show that first of my question is says that what is the sum of the measures of the external angles? Okay, this was my figure. Okay, let me first extend each of my line segments. I would be having like this. I would be having this. No, I am not having this. Wait. If I extend this to be like this, well, if I just extend this to this, if I just extend this, if I just extend this, and again if I extend this. Okay, so it is like a rotating spinner like shape. Okay, so let me mark angles. See, this is my external A. Let me write external A. Okay, and similarly it is my external B, it is my external C, it is my external D, and it is my external E. Here it's my external E. So all these are my external angles. So I have to show what it's given to me, that sum of my all the external angles which I have labeled. So it is basically asking about for E of A plus E of B plus E of C plus E of D plus angle E of. Do you have any issues till now? You may just ask. You may just ask if you have any issues till now, or you may solve the question. It is given that you have to sum up all these and you have to tell me the answer. Okay, just go ahead and try to solve this. I have to add all them up. I would definitely give you a hint. Use that summation of external angles property which I have just illustrated to you. It is a direct question. You have to apply directly, and you may just pop up with the direct answer. Yeah, you may just recall that property and just tell me the answer. What should be the answer here? Can you just guess? See, I have just opted for my angles A, B, and C. All the external angles. I have just sum up all my external angles. Yeah, that was the property, na? Sum of all the external angles for any of my polygon, closed polygon, it would always be for any of my polygons. Let it be, if it be three-sided, it would be four-sided, it would be five-sided, it would be like 37-sided. It won't be mattering since we are considering all the angles, all the external angles. Okay. So yeah, we would be we would be discussing its proof later on while being discussed, but let us now just focus on the application part of it rather being procedural part. So it would be 360. Nice. Okay, so it is my first part of the question. Second part of the question says that it is asking is interesting one, is my angle E of angle A not plus it is given is my all the external angles are equal in measure. Can you just guess, are they equal? All my external angles. Let me give an hint. It is also given, if you clearly observe, I have given you the key to be noted is regular. So it is my regular hexagon. Now think, what would be the answer? Yeah, since all the internal ones are equal, all my internal A, if this is my internal A and this is my internal B, so my A is B equal with C, and which in turn equal with all of the internal ones. Yeah, which in turn they are all of the internal ones. So what would be the answer for the second question? Yes or no? Yeah, it would be yes. Since it is a regular, so all my external angles also would be of equal measure. Okay. Yeah, so let us now move ahead. Yeah, it is all, if it is yes, then you have to figure why it is so. So can you just guess why it is so? Yeah, can you just guess why it is so? See, why it is so is because, do you, for proving this, see, let us consider, you have to go through a concept of what? Linear pair. Should be knowing. If I have a line and if I have a line, let me be quick. Okay, if I have a line and end of the line intersecting over it, and I have two angles, let me call it X and let me call it Y, which would be making with our, see, it is a straight line. So I would be calling, since it is a straight line, I would be calling X plus Y would be what? 180 always. Since if you are having compared with the protector, you would be having here what? 0 degrees. It would be having 10 degrees, 20 degrees, 30 degrees, and up till here would be 90 degrees, and further up till here, it would extend to 180 degrees. So this line, so it represents that this line from 0 to 180 degree, it has measure of 180 degree. Any of my straight line would has a measure of 180 degrees. So that is why, since this is my straight line, so I would be having X plus Y equal to 180 degrees. Seems clear? And if so it is the case, can you just see this and this? See, my diagram is looking very not tidy. All these angles, if I just draw them separately, see, I would be having an angle like this, wherein wait a second. Wherein if my angle like this, if this and further if this and yeah, it is like this. And if I have a line like this, see, I have this line, straight line, so all these internal angles were my equal since it was a regular one, so all these are equal. So my external angles were this and this and this. I just extend here also. This would be my external, this would be external, and this is my external. Since all my internal angles were equal, let me name one of my internal angle to be 1 and any of the external angle to be 2. Since angle 1 plus angle 2 would give me what? 180 degree. Using the same concept, linear pair, they are the linear pair of the lines because they are lying on the same line. See, consider this line to be like this. Okay, it is a straight line, and if it is a straight line, all the angles dividing them would sum up to 180 degree. I don't have any of the third angle which would be forming. Okay, so I would be considering only this one angle, which is my blue shaded angle, which is lying inside of my hexagon, and external angle, which is my 2, and summation up to which would give me 180 degree. And it would be case for all my angles. It would be case with all my angles. It would be case with, let this be 3. Okay, it would be, if it is 3, if it is 4, it would be with my angles. And since my all internal angles are equal, it would be 6 times 10 basically. So if all my angles would be equal and summation of all the internals and the outervals which give me 180 degree only, since they will all form 180 degree. So this would be my always the same. These would be my always the same. Why always the same? The box would yield me what? 180 degree minus the circle, okay, which is my angle 1. Since all are equal. So you may clearly say that external angles, any angle, would be my 180 degree minus of external angle A. And similar is the case with E of B as well as E of C, E of D. All external angles would be equal to 180 degree minus. Okay, seems clear till now. Now doubt must be sorted. Yeah, is it clear? Okay, so it is the case. It would always be like giving to me this. So I can say in regular, my external angles are always be the same. So that was my question number 2. It would be interesting, though I think so. Yeah, now what you have to find, now they are asking to find the measure of my external angle, measure of my external angles, these external angles which I have just found. So if I just determine E of A, I would be having all of my E of B and C and D. So I have to determine just E of external of A angle. So it is nothing but my what? 180 degree. It is would be less than 180 degree times A minus of angle A. So if I just determine angle A, wouldn't my question be solved? Can you just tell me? Yeah, my question would be solved if I just determine the angle measure of angle A. So how would I find the measure of angle A? See, let's go through our image once again. See, I have all my angles are equal. Wait, how would I determine? See, I have a direct approach. I won't be going through finding internal angle. Wait, I would be utilizing here the same concept of summation of my all the external angles. See, so all my external angles are listed here. Okay, so I don't have to, and all the external angles are equal. Let me call it be k. Okay, so if I just add all the 6, if one of my external angle is k, if I just all add them to 6 and all of them are equal to each other, so I would be having 6k, where k is one of my any external angle. Let it be e of external angle a, so I would be having 6k, and I know using the property which is my what, sum of all external angles for what I just did. Are you getting it? What I just did? I have just sum up all my external angles. And why would I sum? Can you guess? Why would I sum? What would I get? I get of any profit? We do anything without any reason. No, we don't now. We would be doing something with the logic, which will give me a better output or a result. So why would I have just sum all my external angles? Can you guess it? Let me give you a hint. Yeah, because to use our summation of external angles property, which I have just discussed. So summation of all my external angles for any of my polygon, which would give me what? How much angle? How much measure? Can you just tell me? It was 3 or 5? 360. You are correct. So 6k equal to 360. So now dividing the equation with 6 would give me k equal to what? 360 divided by 6, which would further give me up to cancellation, which would give me 60 degree. So each external angle measures what? 60 degrees. Seems clear? Each external angle would measure 60 degrees. Okay, so these all my external angles are of 60 degrees. So these are 60, 60, 60. This is a rough sketch. 60, 60. Okay, so we are clear with it. I think so. So let us just move our discussion. Let us now move our discussion to the types of the quadrilaterals. We must be discussing the types of the quadrilaterals, which we must be discussing. Yeah, the types of my quadrilaterals. Types of my quadrilaterals are basically of here. Quadrilaterals being a four-sided polygon. You may be recalling. I just told you in the beginning of the session. See, I have basically 5 types of quadrilaterals. Okay. Number 1 being my parallelogram. Which is having a shape like this. Okay, and let us now discuss about the properties of a parallelogram. It is said that opposite sides are equal and parallel. Okay, I have opposite sides equal and parallel, as well as my second property is about opposite angles, basically opposite angles. Wait, it is just marked. Opposite angles are equal. So opposite angles are equal, as well as bisect one another. Seems clear? So here would be opposite sides are parallel as well as they bisect each other. This is these properties you must have to remember for solving further questions. I would be listing down the properties of there are just the 5 basic type of quadrilaterals which we would be encountering. 5 out of the 5, only 3 or 4 would be asked frequently. So you have to not just and the properties are also of the similar kind. So you must not be panic about the learning, the jot down all the properties. If you got the basic pattern, you would be learning the properties for all the quadrilaterals. Don't be in a hurry, okay? So let us now discuss about rhombus. This is my second type of quadrilateral. See, rhombus, as I have just discussed, was in the mensuration section. Rhombus is like a square brother. It is like brother of a square. Not exactly the square, just a basic difference, a silly difference. You see, all sides are my equal. Clear? First property must be all sides must be equal. Then my opposite sides must be parallel. Clear? Likewise in my parallelogram, opposite sides, there are opposite sides equal. Since all sides are equal, so I would be considering opposite sides only, na? So opposite side must be equal, as well as diagonals are perpendicular to each other. Okay, in this case, diagonals are perpendicular to each other. So it is my case. Okay. Diagonals are perpendicular to each other. Next polygon, which we would be learning about, which is our friend with the school, from the school, which is my rectangle. Let me draw fourth one here as well, which is my square. I don't have to discuss much about these. You would always knowing this property. Opposite sides are equal. Okay, and opposite sides are equal and parallel as well. Each edge make 90 degrees with another edge. It is also obvious. See, this side would be equal to this side would be equal to this side, and each of my angles, this edge angles connecting with another edge would be also 90 degrees. Clear enough? So these are just the basic properties out of another property of a rectangle are diagonals are always equal. I have two diagonals. You may just observe, this would be my diagonal and this would be my diagonal, and these two diagonals would always be equal for any of my rectangle. Diagonals are equal. Seems clear? And the property finishes. So these three properties you must be keeping in your mind. So this is my square. Square means all sides for side friendly. Side friendly are square and rhombus. Okay, just an exception. Rhombus are not having a right angle here. Here they are having acute angle. Here it is acute angle. Here and here, and here and here the angles are more than 90. Okay, so it must be in your mind all the time about the basic properties. These are just the basic properties. Okay, clear until now? Have you any issues? You may just pinpoint at any of the property which I have to just repeat. If you have no issues, we can move ahead. Do you have any issues or something to ask? You may just ask freely. Yeah, so let's move it. So it is a side friendly, so I can say that all sides are equal. All sides are equal, as well as I can also say opposite sides are parallel. Basically, see, if this side is parallel with this side is parallel with this side. Okay, so my opposite sides are equal. Opposite sides are equal. This is how. Seems clear? And I have just enough. I would be having that same diagonal would be equal. All the both the diagonals are equal, and the diagonals are equal, and they must be also bisecting. Diagonals are also bisecting to each other, as well as they make 90° at the point of bisection. Seems clear? Yeah. So these are my basic of the not triangles, quadrilaterals. Okay. So if you are sorted with these 4 quadrilaterals, we will be moving to a last special quadrilateral, which would be asking very rarely, but yeah, it is included in our scope of discussion, so we would also discuss about it. Okay, why would be letting it go? So let us now discuss about the 5th quadrilateral, which is my kite. Yeah, it seems funny. Kite. When I used to learn, I would be like kite. I would just directly imagine a blue sky between which there are many kites, and I would be figuring how kite quadrilateral might be. It would be like this only, as this only. So I would be thinking, and actually it was like this only. So wherein we have our major properties are, see, here we would be discussing for every of the cases opposite. I would always write opposite sides are equal, all sides equals, either opposite side are equal. Here opposite scenario won't be occurring. Here my adjacent scenario would be in what? Would be in talk. So if I have a diagonal, so if I just label this kite A, B, C, D, I would be having all adjacent. Let me write adjacent sides are equal. I have also illustrated that AB, that is AB equal to AD and BC equals to CD. Okay, see, these are my adjacent, means they are lying one after the another. They are not like AD is equal to BC. It is not the opposite case. It is just the adjoining edge is my, okay. So it is that one. So here's another property about the diagonals. It is said that one of the diagonals which we having 2 only, we would be having two diagonals. Seems clear? Diagonals. One of the diagonal bisect the other. Not both will bisect each other. One of the diagonal would bisect the other. So that's why, because of these two properties, the kite is a special type of quadrilateral. Okay, so these are just basic properties about my 5 quadrilaterals. Okay, you have to just keep in mind the following properties, which would be following properties you must be knowing for the further discussion. Until now, let's just pause our session. Goodbye.